Let's find the binomial expansion for f, and then we'll modify that and find the binomial expansion for g. So the binomial expansion for f will look a lot like the geometric series, except that we will have binomial coefficients. We will start with p choose 0. P in this case is negative 1/4. P is the power, plus negative 1/4 choose 1 multiplied by x, plus negative 1/4 choose 2 multiplied by x squared. Generally are looking for 4 non-zero terms, so we'll stop there, plus ... It is a series. Now the first two binomial coefficients evaluate really easily. Negative 4 choose 0 is 1. And then negative 1/4 choose 1 is p. So whatever p is up there. P choose 1 is always p. And now the two that we have to do some work for are negative 1/4 choose 2 and negative 1/4 choose 3. So we start with negative 1/4, we subtract 4/4 and get negative 5/4, and we stop when we get to 2 factors. And technically that's a 2 factorial down there, but it does not matter. And so this is going to give us positive 5/16 divided by 2, which is 5/32. That will be this coefficient. Now let's find the next one. So negative 1/4 choose 3. We're going to start out the same. Negative 1/4 multiplied by negative 5/4 multiplied by negative 9/4. So we do repeated subtraction of 1 until we get 3 factors. And in the denominator here, we have 3 times 2. We have 3 factorial. So let's see what this is going to simplify to. We are going to multiply the numerator together and then divide by 6. So in the numerator, we're going to end up with a negative number. We will end up with negative 45 divided by 4 times 4, which is 16 times 4, which is 64. And then we're dividing by 6, which is the same thing as multiplying the denominator by 6. So now we have to simplify this a little bit, and we see that 3 can go into both this, and 3 can go into there and give 15, and that is going to be simplified. So we will have negative 15 divided by 128. That will give us negative 15 divided by 128 multiplied by x cubed. So now we have our series expansion. And just note that we are not going to be able to write this in summation notation without using the binomial coefficient notation here. There's no other pattern that we could use to describe these coefficients. The only way is with these binomial coefficients, so there's not going to be a concise way for us to write that other than using the binomial coefficients. All right, so now the next thing we're going to do is find the binomial expansion for g. Well, g is related to f in that we just do a substitution. In here, we are thinking about what x gets replaced with. Well, x is going to get replaced with negative x squared. So everywhere we see an x, we're going to put in a negative x squared. So we'll take our expansion for f, and we're going to modify it by putting a negative x squared in for all of the x's. And this we will simplify a little bit. We don't want powers of powers here. That can pretty easily be simplified. So we'll do it. There's lots of times we don't simplify expansions, but in a case where it's super simple, we generally like to. Binomial series expansions are frequently a place that we do a little bit of simplification. So the next term here is going to be positive 5/32. Negative x squared raised to the 2 is going to be that. And then we're going to get another positive number over here because we have a cube on the negative, which will preserve the negative, and negative times negative will be positive. So this is our binomial expansion for G. Now we did a replacement, so that replacement must also be put into the interval of convergence. And I didn't write it up here, but the interval of convergence for this one, based on a p-value of -1/4, is -1 to 1, including the 1, excluding the -1. Once again, we cannot find this with the ratio test. The way that this interval of convergence is found takes a little more math than what we do in Calc 2, so that's always going to be given to you for a binomial series expansion. But once we have that interval of convergence for f, when we find G as a modification, well, we have to modify the interval of convergence. So the interval of convergence started as this. Well, we replaced x with -x squared, so we do the same thing here. Replace x with -x squared and then simplify that inequality. So the first thing we'll do is multiply by -1, and multiplying by -1 is going to reverse the inequality symbols. And then I'm going to write this in our traditional way, left to right, where left is less than the expression to its right. So we'll write it like that. Now, I like to do this with a little algebra trick. You could certainly graph this also. Let's go through both. My algebra trick is to ignore this, because this is always true, right? This is a compound inequality. That left side is always true. X squared is always bigger than a negative number. So really, the solution to the compound inequality is the same as the solution to that inequality. And if we take the square root of both sides right here are non-negative, so we can take the square root of both sides, and this is going to give us the absolute value of x is less than 1. And that tells us that our interval of convergence is -1 to 1, excluding both endpoints. Now we can also get at this graphically. If we think about x squared as a function, so y equals x squared. Y equals x squared looks something like that. I'm going to label some points here. And the question that we're answering is, when is x squared between -1 and 1? So we want to know what are the x values that cause the function values to be between -1 and 1. And if we're being really cautious, we're saying equal to 1 and equal to -1 or less than +1. So we want to know what are the x values that give us y values for the function y equals x squared that are between -1 and +1. Well, if we look at our graph carefully, right, the x values that generate these y values with holes right there and there, those y values are the y values that are between -1 and 1. And those y values go from -1 to +1 on the x-axis, excluding the endpoints. -1 and 1 cause a y value of +1, which is excluded over here. So you can see that the x's that satisfy that are the same x's that we have over here, and the interval of convergence is -1 to 1, excluding endpoints.